University of Alabama. Alex, the floor is yours.
Well, it's my pleasure to, I'll use the microphone, it's my pleasure to share with you some of the activities that we have related to iridium catalysis and supporting molecular clusters of iridium. In general, in my group, I'll start with a very brief introduction. We aim to do fundamental research on single-site catalysts to develop toolkits and understanding that we can then transfer to real materials, which most likely in practice will not be single-site for economic and other considerations, but that nonetheless benefit from the toolkits and understanding that we develop that get us out of the conventional box of thinking and trade-offs that we commonly have in catalysis to new modes of reactivity on surfaces. And so we have several case studies where we've gone all the way from a concept toolkit development to real practical catalysts that are being used. Some of those that are being discussed were discussed earlier today in the biomass session. I want to focus on our work with tetrairidium sites. And so I'll introduce them and talk about our work with understanding environment effects on hydrogenation-related catalysis with those sites. So I really like Stu Solid's work, and in particular this slide, which is summarized in a recent article of his, because it really unites materials science and the design of functional materials with catalysis. And so in the area of HDS catalysis, there is a direct correlation between the activity of the catalyst and the surface area. And assuming a certain shape, in this case a cubic shape, the surface area, of course, is related to the characteristic primary particle size. In this case, if we want a surface area of around 400 square meters per gram for nickel phosphide, then the connection to materials science tells us we need to stabilize nickel phosphide at 30 angstroms. And so immediately then you can see the need within catalysis to stabilize small particles that have defect sites, edge and low coordination sites for catalysis. So our construct, in order to be able to do that and avoid sintering as a common problem, is to put bulky organic ligands on the core, the metal core of the cluster, in such a way that there's a mismatch of radii of curvature. The organic ligands, if they're rigid, and we're using rigid calyx 4 arene ligands in the cone conformation here, have a very high radius of curvature, while the metal core can have a very low radius of curvature, and that can create stable sites that are protected, yet accessible on the sides here, on the lower side and upper side. And so we've had a series of papers where we've demonstrated this materials construct at work. And of course, ultimately our goal is to impact processes like I showed on the first slide, using this as one of the tools in the toolbox. When we got started, we chose tetrairidium cores because of the pioneering work of Bruce Gates in supporting these molecular cluster sites on surfaces and seeing if we can leverage on that with our ability to functionalize these sites with organic ligands. Another interest in using organic ligands is this analogy with metalloenzymes and enzymes that use clusters is being able to tune the redox potential inherent within the cluster and the binding affinity of reagents by virtue of the organic ligand. And so we can start with this parent iridium 4 dodecacarbonyl. We can functionalize it with a calixarine ligand, and then we can look and see whether our construct is working by removing COs and assessing whether we have stability and whether we have a construct like this where the calixarines can stabilize a protected but accessible cluster by serving as the equivalent of a bumper on a little bumper car. And so initially we began this by making the world's first calixarine-bound metal polyhedra and systematically putting 1, 2, and 3 calixarine phosphine ligands on the tetrairidium core. And this is a substitution that we can easily follow by phosphorus NMR spectroscopy. And what one sees is an axial phosphine ligand upon 1 substitution, an axial equatorial phosphine ligand upon 2, and then 2 equatorial and 1 axial upon 3 substitutions. And we wanted to see how many calixarines do we really need in order to be able to stabilize this cluster after we begin taking CO off. So in our early experiments, we didn't even support this cluster. It was just a fundamental question related to Stu Solid's first slide about how do we stabilize small colloids with vacancies. And the way we went about that was just thermal treatment in an organic solvent to see whether we could indeed stabilize clusters with vacancies with these types of ligands. And we followed that with dynamic light scattering and just infrared spectroscopy in solution. With the single phosphine substitution, we saw a rapid loss of stability. So here we are going from 25 degrees C, where we're stable, to 115 degrees C, and we've already lost stability by 115 degrees C. The only cluster that was stable up to 135 degrees C was the calixarine with 3 substitutions. Now, if we look at what happens in terms of COs on the cluster, this is just summarizing the stability that we're observing with 3 substitutions on the basal plane. What you see by IR is that the tri-substituted cluster is the one that's lost the most COs. So this is the bridging CO region. This is the terminal CO region. And here we are by 135 degrees C. There's no more bridging CO left. We've significantly depleted the number of terminal COs. That's very, very different to the monosubstituted case, where at 135 degrees C, we're virtually unperturbed here. There's so much overlap that all of these look like one spectra. On the other hand, this one has already lost stability, and this one, although it's lost most of its CO, retains stability. Now, that trend in terms of more substituted and more electron-rich substituted tetrairidium clusters losing CO more readily is not unique to our system, and it was observed in 1992 here in this work of Atwood, and actually remains unexplained to this day. It's a significant effect in the rate of decarbonylation that spans a factor of 3,500. This is a ligand effect now, and going from the parent dodecacarbonyl cluster to 1 phosphine ligand to 2, there's already a 3,500-fold increase in the rate of CO loss that's attributed to an activation effect. But the path by which CO is lost is not known. So this rationalizes why the more substituted cluster has lost more CO here, but what we find is that even though it's lost more CO, it remains mechanically stable. And so that was our work going in our construct. And so we decided to focus on this tri-substituted cluster. And here is data from crystal structure of that cluster going in. And so you can see the 1 axial phosphine ligand and the 2 equatorial within the basal plane, defined by these 3 iridium atoms that have bridging COs defining that basal plane. And then we have an apical position here that is unsubstituted with phosphorus ligand and containing 3 COs at the top. And that's just a zoomed in view again from the crystal structure where you can see the broken symmetry that wasn't present in the parent dodecacarbonyl, where we have the apical position with the 3 terminal COs, the bridging COs in the basal plane, and then the substituted iridium atoms that we just talked about. So then what we did is went ahead and took that cluster that looked in our preliminary studies to be the most stable and anchored that on the surface of silica. This is just bound through electrostatic interactions where it immobilizes from an alkane solvent, looking like this. And we call this the closed ene because this is an L3 ene because there's 3 calixarine phosphine ligands here immobilized on this silica 500. And we're typically working with 1 weight % iridium. So if you take this material, which is in the closed state that we've immobilized it, and you just flow a gas, it doesn't really matter the composition of that gas, it's a sweet gas. And look in the infrared, you'll see that you're losing both bridging COs from the basal plane, the ones that were shared between 2 iridium atoms, as well as terminal COs by just a simple sweep gas treatment at 40 degrees. And this wing going up shows how reversible it is, that we can take those COs and put them off. That's just demonstrating a basic element of control as we get started. We can go ahead and do a further experiment now where we've taken the sample from the previous slide that's already been treated with a sweep gas and already has vacancies. And presumably that's stabilized by the calixarine ligands being there. And we can flow something that's known in the surface science literature to have a strong affinity to iridium. We can go ahead and flow ethylene, which binds strongly to something like an iridium 100 surface. And what we expect is binding of ethylene. What you're seeing during this flow of ethylene over many hours is continuing decarbonylation. So what you're seeing here is helium flow, and then at around 48 hours we're switching to helium, and then we're flowing helium. And, ethylene. So we're switching to ethylene at this point after creating vacancies in helium. We're switching to ethylene here, and we have further decarbonylation, presumably because ethylene can also be a sweep gas. However, when we do a difference IR spectrum between here and here, the result is we don't see any ethylene bound. And that was very peculiar because we've certainly created vacancies. We've certainly created sites where CO has left, and we know that ethylene can have a very strong affinity for iridium. So this was a surprise, and we began thinking, what are other methods by which we can open up iridium sites? Now, we knew ahead of time from the work of Sonnenberger and Atwood that I put up that with a tri-substituted cluster here on the basal plane, we saw even with 2 triphenylphosphines, in the case of the Sonnenberger data, there was a 3,500-fold increase in the rate of decarbonylation on the substituted iridium atoms. So that when we're doing this simple decarbonylation, a corollary of that is that we're going to be losing COs not at the apical position, but on the basal plane. And that's consistent with almost all of the synthetic chemistry of tetrairidium clusters, which do manipulations on the basal plane. There's very few examples of substitution at the apical position. And that's because its vacancies are most easily created on those substituted iridium atoms. So our thought was, maybe there's another way that we can create a vacancy to experience this high affinity that ethylene is supposed to have for iridium. And so we decided that instead of using a sweep gas, which we postulated decarbonylates where the rate is highest at the substituted iridium atoms, that we would instead try to remove CO from the top apical position by using amine oxide oxidant, trimethylamine oxide, as a bulky oxidant that could access and oxidatively, by a different mechanism than the one from simple decarbonylation, remove the apical COs. Now, when we tried that with a variant of our cluster where this R group was H, in other words, it was a phosphine that was a methyl diphenyl rather than CH2 oxygen of the calixarine diphenyl phosphine, so much less steric bulk with this methyl group than this substituent here. Then we would just get nanoparticle aggregation. And so this result right here, again, reaffirms the importance of the steric bulk of the calixarine giving us a construct in materials like this rather than like this. which leads to aggregation when we have that much of the metal exposed and lack of steric protection. And so on the calyxarine, we could actually do this, and we would have a conjugate where we have that trimethylamine bound to the calyxarine, which we could then remove under vacuum and just have follow this removal and quantify the amount of trimethylamine by NMR spectroscopy. So here's some liquid phase IR data. This is what our cluster looks like in an alkane solvent before trimethylamine oxide treatment. And then after trimethylamine oxide treatment, you're seeing the removal of some terminal COs as well as some bridging. And here's the quantification, that if we start with a normalization of 1 for the amount of terminal and bridging, this would be 6 total and 3 total, then we have 92% of the bridging and 92% of the terminal, 73% of the bridging remaining after the trimethylamine oxide treatment, the way that we were doing it initially. So here we are now doing a simple test where we've done this trimethylamine oxide treatment. We have immobilized on silica, and now we're flowing ethylene. To compare with the one that I already showed you, which is taking a closed sample, creating open sites on the basal plane and flowing ethylene, which did not bind ethylene or an ethyl fragment. And here we see evidence of an ethyl fragment now bound, presumably because we're exposing sites here at this apical position via the trimethylamine oxide treatment. So I couldn't understand or explain why the ethylene and why we were seeing ethyl on the apical so readily in this data here by exposing a site with trimethylamine oxide, whereas we were having so much trouble seeing that with the basal plane vacancy. And that's where we turned to Dave Dixon for help, and he was able to show that there's a significant thermodynamic preference for binding ethyl at the apical position compared to the basal plane. And that the origin of this preference was electronic rather than steric in nature, because this preference remained as we changed in silico the substituents on the phosphine to have insignificant steric restrictions. So this was not brought about by the calyxarine. This was brought about by the fact that we have substituted and unsubstituted iridium atoms, where the substituted iridium atoms electronically do not bind the ethylene. So how is this manifested in a catalytic system? We can run HD exchange on the closed, and there's no poisoning of ethylene, because the sites that are doing the HD exchange and the sites that are exposed are the ones that are on the basal plane. This is all just getting to know our system. We're just getting started here. When we try the same experiment with the open and something that's been opened with one equivalent of trimethylamine oxide, now you can see that ethyl is a poison, and that gives support and credence to the FTIR result where we saw ethylene binding when we did opening with TMAO. And so now when we go to do catalysis, we see the result that frustrated mutaries and many others who have done or attempted to do catalysis with clusters is that here we are with our closed. We know that we're opening sites on it just by flowing hydrogen and ethylene, but the catalytic activity has an intercept going through 0, 0, and it remains very, very low. Again, this is even despite the fact that we're removing a significant number of COs during this flow. Here's in situ IR evidence of how we're removing COs, presumably on the basal plane, in this closed system. On the other hand, as soon as we open up that apical site and we have ethylene binding by infrared spectroscopy and poisoning of HD exchange, we immediately have the onset and a non-zero intercept for catalytic activity. So then we decided to see how can we improve this further. Can we use, for example, a more bulky oxidant to try to increase the amount of terminal CO that's being taken off at the top? We didn't see an effect. That was perplexing to us. We came up with a different procedure, though, where, based on templating and imprinting literature that I became familiar with during PhD, we decided to actually create the open site in the presence of ethylene, thinking that instead of leaving it completely vacant and exposed, if we occupy it with the reactant that we're essentially going to hydrogenate later, we can create a more stable site for further manipulation. And so here we are doing the same trimethylamine oxide treatment, except in the presence of the ethylene. So here's the data that I showed you previously. When we treated with trimethylamine oxide in solution, we see some decarbonylation of terminal as well as bridging CO. But now, when we're doing this decarbonylation in the presence of ethylene, the proportion of terminal that we're removing has changed and increased. And so instead of being left behind with 92% of the terminal CO, we're now left behind with 81%. And that got us excited as potentially good news, because we know only the basal plane unproductive sites contain bridging. And so by shifting to terminal, that potentially may indicate to us that we're decarbonylating where we want. But the more important thing that this perturbation gave us is an ability to assess what kind of a job we're doing at removing CO where it counts at the apical position. Because the catalytic activity now with more terminal decarbonylation has increased from this value here to this value, and we can go ahead and analyze at time 0 on stream at the y-intercept and make this plot about how the initial turnover frequency is varying as a fraction of the terminal CO removed using trimethylamine oxide. And what you can see is there's a direct relationship that goes through 0, 0. And what that tells us is that all along with trimethylamine oxide, 100% of the terminal CO that's being removed is coming from the apical position. It's already selective. If that wasn't the case, we wouldn't be getting this kind of a direct correspondence. So now we can view this as a new type of single-site catalyst. We can view this as a catalyst where we have a productive site that's able to bind ethylene and catalyze its hydrogenation at the apical position. And we have in this simple model system of a metal surface the ability to place ligands not at the site where catalysis is happening, but nearby on the nearest neighbor metal atom. And so this is an ideal system for looking at ligand effects at a distance, which is an emerging area of catalysis and catalytic understanding. And so that's what I'm going to start talking about next, is how does changing what's here on the basal plane influence reactivity that's happening up at the apical position. So one ligand that we can make to take a big jump in terms of electronics is, instead of having a phosphine, which is connected, phosphorus connected to 3 carbon atoms, we can go to a phosphite while still preserving the steric protection afforded by the calixarine, where the phosphorus is now connected to 3 oxygens. What that results in is, by nothing more than a little design and a little bit of luck, exactly the same substitution pattern on the cluster. So we're still looking at 1 axial phosphite ligand and 2 equatorial phosphite ligands. That's important because we're not changing the connectivity within the cluster when we're making a comparison now between phosphite and phosphine in order to learn what is the role of this ligand change. We're keeping the coordination environment exactly identical, and we can tell that from the phosphorus NMR. The result is a blue shift when we go to the more electron-accepting phosphite due to the oxygen substituents. And that blue shift you can see here in this dotted spectrum for both the bridging and the terminal region of the closed cluster. We can go through the same manipulations of opening up with TMAO the apical site on the phosphite, and now we see about a 2.5-fold increase in the catalytic activity when using the phosphite rather than the phosphine. And that seems to be similar to the increase that's reported in a phosphite-phosphine comparison by Bill Jones, also for alkene hydrogenation, and he attributes this to ease of alkene reductive elimination. as the rate-limiting step. So here's an example then of organic ligand control of catalysis from a distance near the active site. We went ahead and made all the different variants that you could imagine, including this chiral one. This is topologically chiral because we have a phosphite in the axial position, a phosphite in the equatorial position, and a phosphine in the equatorial position. Phosphine being in red, phosphites being in blue. You can go through and generate a series of different substitutions ranging from all phosphine, all phosphites, or the two mixtures in between, having two of one and one of the other. As we did that, we changed the terminal CO frequency as well as the bridging CO frequency in the manner that can be rationalized by my logic on the previous slide, that the more phosphite we add to the series, the more electron withdrawing character we're adding to the ligand set, and the more we're blue shifting the COs in this direction. But what you can see is that ethylene hydrogenation only cares about the first phosphite. It doesn't care about the chirality. It doesn't care whether we go and make all three phosphite substitutions. Within this set of two equatorial, one axial ligand, even though we're changing the electronics of the cluster, catalysis only responds to that first change. Then we decided to do a different ligand change because we wanted to see whether we could significantly increase the activity of these clusters with an oxygen treatment and move away from the electron-rich character that's being imparted by our phosphorus ligands. This is what happened when Igor, first in the lab, went ahead and did a catalysis treatment followed by oxidation, which could just be done with oxygen or dry air. The important thing is just to keep the system dry. And then followed by a second ethylene hydrogenation. And we see about a 100-fold increase in the catalytic activity compared to what we have here from the closed cluster. This 100-fold increase can't be elucidated or understood or substantiated by just creating an active site on the top by CO oxidation there. So this argues for an additional ligand effect, one that isn't covered in the series that I just presented with the organic ligands. This argues for a ligand effect with molecular oxygen. We can monitor this process by in situ IR spectroscopy. So now here we're looking at the terminal CO intensity. And so here we are losing terminal CO in that first ethylene hydrogenation. We're getting hydrogen to bind as hydride to the cluster. CO is leaving. Oxygen treatment goes into two compartments, two regimes. One where we're oxidizing those bound hydrides to water and binding oxygen very strongly to this electron-rich cluster in the way that we would have predicted from Norskop's calculations on gold and other related metals, that an electron-rich metal of this sort is going to interact with oxygen very strongly, followed by a slower process indicative of CO loss that is corroborated by X-ray absorption spectroscopy. Here we are doing our second ethylene hydrogenation, where we're losing a little bit more CO, but now we're recarbonylating, and we're saying, let's give as much opportunity as we can to repopulate those sites that have been occupied by hydrogen and possibly by oxygen in this treatment step with CO. And as you can see, the system only goes back to where it left off after oxygen treatment. Those oxygens are bound very, very strongly in this electron-rich L3-ene cluster on silica. L3-ene being all phosphine on the basal plane, and there's three of them. This just corroborates what I said here. This characteristic blue shift is due to oxidative addition of hydrogen as hydride on the cluster. Oxygen treatment takes that off. Here's the second ethylene hydrogenation, followed by recarbonylation, taking and displacing the hydrogen off again on the surface with CO. All of this is saying that CO in this final step of recarbonylation cannot undo what was done during this oxygen treatment, in which X-ray absorption spectroscopy shows we have two dioxygen ligands bound to this cluster in a persistent manner. Even if we do here a hydrogen treatment to try to reduce off those bound oxygens, we still can't recarbonylate. We cannot take those oxygens off of this cluster. They're bound very, very strongly. And again, consistent with DFT calculations that predict very strong oxygen binding on these types of highly electron-rich clusters. So what happens now if we look at ligand effects within this catalysis, oxidation, catalysis treatment? Presumably the story here in terms of that 120-fold rate acceleration that we're seeing is this is an effect of persistently bound dioxygen ligands. We have a hypothesis on how they're bound that's supported by X-ray absorption spectroscopy that's consistent with this IR and that we're putting together right now. But I want to shift gears and look at ligand effects within that series. So let's go back to the more electron deficient cluster of the L3 phosphite, which we previously saw shifts CO to the greatest degree in terms of a blue shift due to the high accepting capability of those oxygens on the phosphite. And so what you're seeing here is there's no change. The data is in blue. Catalysis, oxidation, catalysis. The phosphite is unchanged in the same regime that the phosphine just underwent a 100-fold increase. That suggests that by making the cluster more electron deficient, we've been able to essentially weaken what we experienced as a very strong interaction with dioxygen previously. Further data for that can be seen by in situ IR spectroscopy that now, during the last recarbonylation step, we're able to recarbonylate nearly all of the CO that we had initially before we began the experiment, after we treat with oxygen. And so compare that now to the case where we had the L3 phosphine cluster on silica, where we weren't able to do this decarbonylation beyond the range of where the cluster was after oxygen treatment. Now we're able to go all the way back to the initial state. And in fact, we can go back to the initial state just by increasing the temperature during recarbonylation up to 80 degrees C, and we can get up to 100%. Those last couple COs require that. So here's a new cluster that we just crystallized. It's an L3 phosphinite, where around the phosphorus now we have two phenyl groups and an oxygen of the calixarine lower rim. So you can probably best see that from the crystal structure here. Here's the phosphorus, here are the two phenyl groups, and here's the oxygen of the calixarine directly bound to the cluster. So this is something in between a phosphine and the phosphite. The phosphine being the one that interacted very strongly with oxygen, the phosphite showing negligible interaction with oxygen, and we were able to take the oxygen off very easily, and in fact it wasn't even on during catalysis. There was no ligand effect of bound oxygen during catalysis. So we might expect this to do something in between, but there's one more crinkle that I need to be transparent with you about, and this is why I didn't use this analogy in this cluster earlier, is because this one does not form, and we can tell this by phosphorus NMR as well as the crystal structure, with the two equatorial, one axial. They're all three equatorial. And so we're doing two things here. We're changing the coordination environment as well as the nature of the ligand. And you can see that here. These are all three in the basal plane of the 1, 2, 3 substituted triangle of iridium atoms here in this phosphinite. But now what we're seeing during catalysis, oxidation catalysis, is a very, very sharp increase in the catalytic activity, suggesting that oxygen is persistently bound on the phosphinite, and that we're somewhere in between, holding on to it very tightly, as the phosphine did, and not holding on to it at all, as the phosphite did. And that this medium ground results in a catalyst that's about 6-fold higher than the activated after oxidation form of the triphosphine-bound iridium cluster. So this is the best that we've had till now, and now we're over here and on par with the activity of just naked iridium-4 clusters that have been decarbonylated at 400 degrees C on supports like MGO. We're actually slightly more active than that. So what I hope to show in the toolkit that we've been developing is that organic ligands can turn on and off the binding of reagents at a metal cluster site. I've shown you an example of ethylene not binding on the basal plane, where we have a substitution by an organic ligand, but binding in the apical position where there is no substitution. Even more recent and exciting to me is this ability to turn oxygen binding on and off by changing the electron richness of the metal cluster and favoring binding of oxygen when we're more electron rich and turning it off completely in the case of the phosphite when we're more electron, when we have a more poor electron donor in the ligand, better acceptor. After oxygen treatment, the electron-rich metal cluster disfavors bonding of CO to the metal core when comparing the L3-ene to the ite, while favoring the binding of oxygen. We discussed that, and that we have significant effects of organic ligands between this inite and the ene during a catalysis oxidation catalysis treatment, where the bound dioxygens really benefit from not being bound too strongly, as they are in the phosphine case, and with some intermediate ground. And so one of the things that we're going to go back to is this series of mixed ligands where we can control systematically that CO frequency by having a combination of varying donor and acceptor ligands, and seeing how that plays out within this oxidation treatment. I'd like to acknowledge a very talented group of diverse people who have done the work. Daniel Ertler is the latest postdoc who has done a lot of the breakthrough synthesis that I described on the inite and on all of the mixed ligand systems. Andrew Palermo has led us in situ IR spectroscopy. Igor Busigin is the person who discovered catalysis oxidation catalysis, and something that we've been able to characterize by X-ray absorption and also by DFT, where we can rationalize that these persistently bound dioxygens really do significantly increase the rate by decreasing the activation barrier for the rate-limiting step in ethylene hydrogenation. This has been a collaboration with Professor Gates, and I'm very much indebted to his expertise and sharing of knowledge in this area, and also to Chevron for funding. And we benefited from a DOE BES team that included myself, Ilke Arslan, and David Dixon. So thanks.
Thank you, Alex, for a wonderful talk, and the floor is open for questions. Yeah.
So you played with phosphine and